about free electron lasers, but I would like that you take home a message on how free electron laser can be used and how this use can be exciting, okay? So we are basically here right now. You see the synchrotron, and this is Fermi, the free electron lasers. You know that free electron lasers are producing pulses, short pulses in time in a region which goes from the infrared to the hard X-rays. And I will, at the beginning, try to convince you that it's quite interesting to use free electron lasers. And then I will spend a lot of time on nonlinear optics, because you have high intense pulses, and if you have high intense pulses, you can go in the nonlinear regime. And then a little bit about phonon dynamics and some future challenge. So why free electron laser? I like this slide because I was watching an episode of this Big Bang Theory that maybe you know better than me. And I think the series was the third one, so it's quite old series. And you see that Leonard is coming back home, very tired, because he was doing free electron laser measurements on using diffraction, okay? And this is the main reason why free electron laser have been built in the last years to do diffraction experiment from proteins, okay? So now let's put a slide which is a little bit more professional. So here you have the pulse duration of your pulses as function of wavelength or energy. So if you concentrate on this high photon energy free electron laser, basically you can cover this region here. You saw a talk this morning from Riccardo Cucini. He was telling you about HAG laser, okay? So you see these two. Then you have synchrotron. You saw from Martina that you can do pump and probe experiments, so time-resolved experiment also with synchrotrons, then low energy free electron laser and conventional laser. Let's concentrate here. So you see that they are complementary, but even if they have a common region, in the common region they are complementary again, because HAG they can go up to a repetition rate in the range of megahertz, while free electron laser they can't. But at the same time, free electron laser, they can go at much higher energy per pulse, while the HAG, no. We are talking about, for example, here, HAG in the range of 10 to the 6 photon per pulse, free electron laser 10 to the 13. So many orders of magnitude. And then free electron laser, they can cover a lambda wavelength region, which is much shorter. And this is important because the wavelength basically is giving you the resolution of your measurements, okay? And we will see a few slides next to this one talking about the importance to measure at short lambda. What I will tell you actually during my talk, which is to me quite interesting, is, as I said at the beginning, experiment using nonlinear response from your system. And you saw already from Martina the advantage to work at shorter lambda or higher energy is also due to the fact that you can go resonant with core-hole excitation in your system and do resonant experiment. And this is important to have chemical selectivity in your experiments. I forgot to say that you can stop me whenever you want. Because I would like to give you my view, but I would like that you get it, my view, because otherwise, it's completely useless, my talk. So, here you have a list of Nobel Prizes given to people working in studying structure from protein, okay? You start from here. In 1946, basically, he was able to crystallize protein, and then you keep on going until a few years ago, where people was able to measure, for example, here, the ribosome structure, and so on and so forth. So why is important to determine the structure of protein? As maybe you know better than me, but basically because the structure of the protein is strictly related to the function of the protein, okay? So how you do it normally? Usually you do X-ray diffraction. So you take a crystal, which is quite large, then you do diffraction with X-rays, Lowe diffraction. So with the X-ray you go on the crystal, then you get the spots. The spots here are telling you the intensity scattered from some plane of your crystal, which is related to the electron density map. If you have a given distribution of electron in your plane, then you will have this point here, or this point here, and so on and so forth. So you can reconstruct the electron density map. Once you reconstruct the electron density map, you have an atomic model, because you know how the electrons are distributed. Then you have an atomic model, and then you see if the atomic model produces this diffraction pattern. So far, so good. I mean, this is well used in synchron. You saw many of the Nobel prizes were coming from using X-ray. And the main problem is that proteins, or better, not all proteins, or the majority of proteins cannot be crystallized, as well also other biological samples. And if you take, for example, membrane proteins, less than 0.1% of this protein can be crystallized. So the main point why one needs to crystallize protein is due to the fact that, in principle, you could put a single protein in the beam, but usually a synchrotron has not enough flux to see any signal from the single protein. So you put together in a crystal in a way such that you have kind of multiplier. So you are multiplying the signal from the single protein times the number of proteins that you put in the crystal, which means billions of times, okay? So that's the main point. You cannot crystallize all the protein, but as I said, you could do it if you have enough intensity from a single object by doing what is called usually coherent diffraction imaging. You put an object, you have your coherent beam, the object will produce a diffraction pattern, and the diffraction pattern encodes the information concerning the structure of the object. If you have a not good coherent beam, then you will get some diffuse scattering at a given angle. But if you have a nice coherent beam, transversal coherent beam, also longitudinal in some case, then you will have some structure, and the structure are related to the structure, the diffraction pattern here is related to the initial, to your sample. Basically, the resolution that you can get here is given by lambda. That's why you need to work at short lambda. One problem is that when you do this kind of experiment, you get the diffraction pattern, you know the intensity of your rays, but you don't know the phases. And to understand how the object is done in its structure, you need also to know about the phases. For example, I have this funny slide here where you have two Nobel Prize guys here that were developing a code to understand how to recover the phase. And if you look to these two pictures and you look to the two below, this picture here has been obtained by taking the intensity from this and the phase from this. And this has been obtained by taking the intensity, the intensity of this and the phases from this. So this is telling you that the phases are the dominating in the scattering, not the intensity. So it's very important to reconstruct your object. So usually has been, what is usually used in experiment doing coherent diffraction imaging is this iterative approach. You have your sample. In this case, this is a real experiment, okay? This is some biological stuff I don't remember. So this is the image of your sample that you can measure even with some other technique. Then you get the diffraction pattern. So you say, okay, I know the intensity. I just make a guess about the phases. But my guess has to be such that the sample that this is scattering is inside this support, okay? In this way, you can Fourier transform your guess, and you try to get the image. If it doesn't work, you have to iterate this procedure, okay? And then you can even change the support during this iteration, and you see after 1,000, 2,000, and 3,000 iterations, then you get your object. So far, so good. And people, basically, almost 20 years ago, they were saying why we do not apply coherent diffraction imaging to image the protein. So I can send a single protein in the beam, I can take a diffraction pattern, I can do the phase retrieval, and determine the structure of the protein. And the idea to use free electron laser is due to the fact that you have your pulse coming here, you hit the protein, then you get the diffraction pattern, but the intensity on the protein is so strong that afterwards the protein is destroyed, but you don't care because the diffraction takes place before the protein explodes, okay? And this is the main reason why all over the places people was building free electron lasers. This is in Japan. This is LCLS, a project in Stanford, California. And this is the European FEL, so also Italy and other nations in Europe were contributing to the construction of this monster. Let's say you start from Hamburg here and you end in Schenfeld, which is this another region. This is 3 kilometers tunnel, 1.5 billion euro. It's 10 times what we paid for Fermi, okay? And now I show the single protein diffraction results. You can see them in this slide. So far, there is not a single protein diffraction result. Just because, let's say, the FEL is starting to work right now, but in reality, the number of photons that you would need is even higher than what you can produce from a free electron laser. By the way, people was measuring nanocrystals of proteins. So this is not a single protein. Basically, here you have a setup which allows you to a nozzle, let's say, which allows you to send the protein inside a liquid, and then you can hit the protein with your free electron laser pulse, and then you get the diffraction image. But what you're measuring are nanocrystals. You cannot measure with the synchrotron because you don't have enough intensity, but you can do it with the free electron laser. So at least you can do this kind of experiment. For example, this is a Nature that came out a few years ago and now has got more than 1,000 citations. So I mean, it's kind of interesting stuff. And this is the structure they were reconstructing. This is a photosystem 1. And basically, the number of data, if I remember well, was in the range of 300 terabyte. Okay. So I don't know if you know how a free electron laser works, but I just want to show this slide here. Usually, what you have a linear accelerator where you accelerate electron bunches. Then you have a magnetic structure which produces the FEL radiation. How it is producing the FEL radiation. This is the bunch at the beginning of the magnetic structure. Then the bunch produces radiation. After a given path inside the structure, then you will have the interaction between the electromagnetic field and the electron bunch in a way such that you get this micro bunching. Okay? And at a given point, the micro bunching is perfect, and when you have a shot noise, you will have self-amplified spontaneous emission. Another way to produce micro bunching is to, I just tell you that this small LINAC is basically 2 kilometers in Hamburg, okay? So this is just a sketch. And this is basically 500 meters in Hamburg. So another way to produce the micro bunching is to do what is called seeding. Basically, before entering into the radiator, you seed the electron bunch with an optical pulse. So you give an energy modulation. This energy modulation, through some magnetic trick, can be transformed in longitudinal modulation. And the advantage is the following. This has been demonstrated a few years ago using a tabletop laser, basically, or close to tabletop lasers. Here you see the seeding emission, very nice. And here you see the SASI emission multiplied by 5 orders of magnitude. So having a seeding is much better. You have a pulse which is very close to a tabletop laser. But this, you can do it at low energies. You cannot do in the X-ray. And actually, the first who demonstrated you can do it in the soft or VUV or soft X-ray were us, basically. We showed already from a few years that you can do the seeding at Fermi. Basically, the red line is the seeding pulse, the optical pulse, and the blue line is the emission of the laser. Here you have some parameters, the time duration of the pulses in the range of 100 femtosecond. Then you have, I don't know what's going on with the microphone. Then you have the energy, where you can do the experiments, and you can have a total control, thanks to the seeding, on the pulse energy, time, shape, and polarization. Okay? As I said, it's like a tabletop laser. In reality, maybe, I don't know actually. Okay. Let's see. I can shout more, then I will end without voice at the end. So I was saying, I mean, this is kind of laser, but if you want to change some parameter, it's kind of or more tricky. I mean, it's not so easy. Anyhow, we have a laser, and the first laser, optical laser, was invented or constructed by Theodor Neumann in 1960. Okay? And after this invention, you had a lot of Nobel Prizes concerning lasers, starting from the theory, who allowed this guy to develop a laser, going to holography, nonlinear optical effect, and so on and so forth. And here at the end, I put also a Nobel Prize in chemistry, because Ahmed Zewail wanted to develop the technique to do femtochemistry using tabletop lasers. Now, if you have some good idea, maybe you can get the next Nobel Prize on using free electron lasers. But anyhow, as I said, I want to talk about nonlinear stuff. And you saw that the first laser, I mean, was produced in 1960, May 1960. And you see this paper is dated 1961, August 1961, where they observed second harmonic generation. So second harmonic generation is a nonlinear effect. You can see the spot of the laser, and near the second harmonic spot. Can you see it? No? The main problem is due to the fact that the physical review editor was thinking that the second spot was just a stain in the paper. It was removing it. So you have two take-home message. Never trust physical review letter editors. And nonlinear effects, I mean, are pretty easy to use if you have enough intensity. I mean, we are talking 1 year later, they observed nonlinear effects. So some year later, Nicholas Bloembergen was getting a Nobel Prize concerning all the developments on nonlinear optics in the optical regime. And basically, this is the formula which explains you basically everything. The polarization, usually when you do an experiment, oscillate at the same frequency of the electric field. But if the electric field is higher, or you have different electric fields, if you prefer, then it can oscillate. I mean, it can oscillate also at other frequencies, which are a combination of the frequency of the different fields. So EJ and EK, they can be also the same field, okay? And usually, I mean, the problem is that usually you don't observe second order effect or third order effect is due to the fact that the intensity that you use are pretty low, and the susceptibility coefficient here are very, very small. But when you have a laser, then I mean you have an advantage. The field that you can use are pretty high. So this is the only equation basically that I put in my presentation. If you take the second order effect and you put E1 and E2, two electric fields, you end up with this formula for depolarization. This is telling you that the polarization can oscillate at different frequencies than the one of the two fields. Basically, the double of the frequency, so second harmonic generation, the one we saw before, some frequency and different frequency. Your polarization can oscillate at these different frequencies. So far, so good. You have a question? Don't hesitate. I mean, stop me whenever you want. Basically, the idea is I have two electric fields, two pulses, if you want. They go on the sample. And what you can produce out of this is a field which can oscillate, as I said, as a second harmonic generation, some frequency, omega 1 plus omega 2, and the difference. There is also this effect, but I don't want to discuss this. So Another advantage, the first advantage of nonlinear effect is the intensity. If you look in angle, the intensity which is produced when you do nonlinear experiment goes like this function here, which is a sink, okay? And basically, the width of this is related, basically the intensity is non-zero when the sum of the wave vector is 0. And this is usually called phase matching, but I like to call it diffraction. Because when you do nonlinear experiment, you are doing diffraction experiment, basically. When you do second order processes, if you have a centrosymmetric material, the intensity that you get is 0. We will see this in the next slide. This means that you need something which is non-centrosymmetric. You can have nonlinear crystals, as the one we saw at the beginning in this paper without the second order harmonic spot. Or you can have, for example, surfaces. If you look to the surfaces, if you look from here, is one thing. If you look from below, is another thing. So it's non-centrosymmetric. That's why people was using tabletop laser, second harmonic or some frequency generation to measure, for example, to do imaging of biosystems, biological imaging, because you can really get information about the surfaces, okay? The reason why, only non-centrosymmetric materials that give a second order term in the polarization is basically written in the formula I was showing you before. If you change sign in the electric field, this part changes sign as this part, but this part no. So it has to be 0 if you have a centrosymmetric material. So we have done a first experiment very recently, as you may see here from the publication, using the free electron laser. So you go with your free electron laser on a graphite sample, and you are looking if you have any second harmonic generation close to the carbon K edge. Okay? This is the carbon K edge. You start to measure in different points. Let's concentrate on this point, and you measure the second order response. This is a real spectrum. This is the fundamental, the energy that you are sending with the free electron laser, and this is the second harmonic signal. So if you look here, for example, in this point, then you see that the second harmonic response goes nonlinear. And this is normal because it's a nonlinear effect. Then you see there are many points, many colors. The difference in the colors are just the sample thickness. So this is telling you that the signal that you get is only from the surface of your sample. So actually you are not measuring the response of graphite, but you are measuring the response of graphene, because really you are getting signal from a single atomic layer. So if you do absorption measurements, you know that you can get information about the structural and geometrical configuration of your sample. In this case, you can measure the local geometric and electronic structure by using this kind of technique by scanning an absorption measurement, an absorption edge, okay? And there is a guy who took a Nobel Prize in 2000 who was always saying the interface is the device. So if you can characterize the interface, it means that you can understand how your device is working. Okay, this is just to tell you that measuring XFs or absorption spectra, you get the information, and this is well known, but just to recall you that you can do absorption measurement to measure the structure, electronic structure and real structure of your system, because the photoelectron will interact with the atoms surrounding it. Okay, so as I said, you can measure graphene. Graphene has been used to build a number of electronic devices for solar harvesting or whatever. But what you can do also is to measure, for example, catalysis at the interfaces. You know that many catalytic processes, they take place on the surface. Then you have a surface, a liquid, or a surface and a gas. So you can measure the electronic behavior at the surface, really on the single atomic layer. And this is kind of nice technique. As I said, the measurement was done really recently, so we didn't do a real scan of all the energy, but already taking our paper, people from APS, for example, from the American Physical Society was writing a non-technical paper citing our results, and also from ACS, the American Chemical Society. So this is just to tell you that this kind of very interesting stuff. Okay, so let's keep on carbon, because graphite is carbon, and Nicholas Broenbergen. He was writing a news and views on Nature entitled First Light on Fluid Carbon. Okay, this work basically was using data taken and published in Physical Review B at the same year by the group of this guy here. And the idea was to do pump and probe measurement on carbon using a tabletop laser. So you pump with one pulse and you probe the evolution in time with a second pulse. And in particular, one way to characterize the sample is to do reflectivity measurements. So here you have an increase of the intensity going down of the pump pulse. As you may see, at a given point, when the pump pulse is coming, the reflectivity increases and stay on even if the pulse is completely gone. So people were saying, you know, here you have a metallic system which is changing its phase and is liquid, using simulation and so on and so forth. So you use a free electron laser, you pump with the same intensity here, and you probe at higher energy. What means higher energy? You are higher than the plasma frequency. And then you don't see any difference, any increase in reflectivity, but you see something which is related to expansion. And the problem here is that when you use as a probe a tabletop laser, you have the plasma which has been increasing to the first beam, and then you have the plasma mirror effect. So in reality, what they were looking here in increasing reflectivity due to the fact you are populating more electrons in the plasma state. Okay, so I don't want to say that this paper was wrong, but this maybe was not correct. Okay, so as I said, another way to measure the properties of your system is in a pump and probe configuration is to measure the absorption edge. Here you see, for example, a measurement done on amorphous carbon, a foil. The continuous black line is what you get from databases. The points are what we have been measuring from the free electron laser without pumping the system. And the blue line and the red line have been obtained by pumping with a tabletop laser. Okay? Let's concentrate on the blue line, so which has been obtained after, I remember, 100 femtosecond. This is telling you that in 100 femtosecond, you have a transition in your system. Since you have this peak here, which is the sp2 peak from carbon, the system is still solid. And the only structure of carbon which has a less intensity here, which corresponds to a less density of states of electronic states, is graphite. So in 100 femtosecond, less than 100 femtosecond, you have a transition from amorphous carbon to graphite. And this is the fastest phase transition I ever observed. Okay? So let's go back to nonlinear optics, and I just ask you if you have any question. Everything is fine? You want to go for lunch, right? So we saw how many frequency can oscillate the polarization when operating on the second order. If you go with the third order, you have many more possibilities. Okay? I will concentrate on one of them, and actually one special case of this, where omega j and omega k are the same. So now try to stay with me if you are interested. You have two pulses, two identical pulses that go at the sample position. If you write down an equation for the electric field, electromagnetic field, you will have a standing wave. So at the sample position, you have a standing wave. This standing wave, through some mechanism, which can be optical absorption, can become a density modulation of your system. Why? Because when you have the top of the standing wave, the electric field is at the top, then you will have optical absorption, then the temperature of your sample will increase, and your sample will expand a little bit. And then you will have this density modulation. Or if you prefer, you have modulation of your refractive index. Okay? Then you use a third pulse, delayed in time, to monitor the evolution in time of this density modulation. This is called transient grating because the density modulation that you have is kind of grating because the refractive index is changing, but it's not permanent because the difference in temperature between the top and the bottom of your grating is not big. I mean, it's in the range of 1 degree during. I have to give you some number. It's in the range of 1 Kelvin, but I mean, it can be even higher or even less. So you imagine that you have this modulation. This modulation will evolve in time, and one of the evolution is through phonons. So you will see this modulation breathing, and then after a given time, you will have diffusion, heat diffusion. Okay. So now you have to motivate why we want to develop this kind of technique. And I motivate this by telling you something about a challenge that many physicists are facing in these years to measure, for example, collective excitation in disordered systems in what is called an explored energy and momentum region. So collective excitation are phonons, density fluctuation in your systems. Disordered systems are liquids, gases, and so on and so forth. And omega and Q are nothing else the energy and the momentum of your phonons. Usually you do this by measuring the dynamic structure factor, and you measure the dynamic structure factor, again, usually measuring scattering from your sample. So you go with your photons on the sample, you measure at given angle what's the energy of the scattered photons, and if you have you are exciting phonons, then you will get two lines here, because the dynamic structure factor is nothing else than the Fourier transform of the density fluctuation in your system. If I have a plane wave, I will have a line here. If you have a crystal, you have two delta function. But this is not a crystal. This is a real spectrum from fused silica. And then you have something which is not a delta here, and you have some elastic line to do the topological disorder of your system. So if you take the momentum transfer, this is related to the frequency of your phonons through the sound speed. So this is Q in a scale which goes from the macroscopic to the microscopic scale, and this is omega. So if you take two typical sound speed, you see here, this is typical from a gas or from a low density fluid, and this is typical from a glass, okay, like vitreous silica. As you may see, there are several techniques which measure this, but there is no technique capable to measure here, okay, not to measure here. And for example, if you take this spectrum here, this has been obtained here by using Brillouin scattering. If you use inelastic X-ray scattering, you get spectra like this one. As you may see, the two nice side bands now are kind of shoulders. And the main problem here is that you have a resolution issue, and also you have the disorder which start to take place, I mean, in a strong way in your spectra, because the disorder usually is in the range of the nanometer scale. The region here that I put this yellow circle is very interesting, because it's if you take Q and you take 2 pi over Q, this is in the nanoscale, 1 to 10 nanometers, which is kind of interesting scale, as we will see later on. So why we want to study disordered systems? If you ask to Wikipedia what are the open problems concerning condenser matter physics, you end up with these 4 points, okay? The first one is amorphous solids, so gases. The second one is for sure high temperature superconductors. Then you have sonoluminescence and turbulence. 3 out of 4 are dealing with disordered systems. And moreover, if you take liquids or glass forming system, those systems are very interesting, because, I mean, for example, you cannot frame the phase transition in the classical framework of phase transition, because you cannot find an order parameter which has a critical behavior at the glass transition. So why you want to study this at the nanoscale? I'll just take one example. I take vitreous silica, and I show you at least a selection of papers that were coming out in the last years concerning the study of phonon excitation on vitreous silica. You start with these two physical review letters, one after the other. The first one, this one, was saying, okay, you know, the excitation are basically localized. And the second one, they're propagating. Funny enough, is the fact that the two groups, they were measuring the same sample on the same instrument. So this is telling you that the limit is the model that you are using. Or you can use the model that you want to determine the properties that you want, because you don't have enough resolution, or the technical problem are such that you can fit with whatever you want. It's important to determine the vibrational spectrum of systems, because this is related to the thermal properties, like for example in solids, but especially for glasses, because you can shed light of open problems like or open question concerning, for example, the plateau in the thermal conductivity of the excess in the vibrational density of states. So I skip this one. I hope I convinced you that it is important to measure vibrations here. If I didn't convince you, at least I was able to convince the European Research Council, who was funding a project about 2 million euro to build an instrument capable to do this four-way mixing, this transient grating spectroscopy using free electron laser. Why we do need free electron laser? Because the momentum transfer is related to the lambda. Okay? So if you want to access this region here, you need the lambda typical of free electron lasers. This is a typical spectrum obtained by using tabletop lasers. So as I said at the beginning, you create the transient grating and you probe the transient grating with another pulse. And in time, what you get is kind of breeding of this transient grating, which is due to phonon excitation. As you may see here, this is nothing else than phonons in your system. Then at a given point, you will have a diffusion. So the transient grating will be washed out by diffusion. So in the visible regime, it's easy. I mean, it's not so easy, but it's easy to split a beam, to recombine the beam, to focus, and so on and so forth. You can use lenses, diffraction masks. And when you go at shorter lambda in the VUV or soft X-ray, this is not so easy, because all the optics, they should work in reflectivity condition. So that's why we started to do an approach, conservative approach. So we decided at the beginning to split the FEL beam in two using the edge of a mirror. So you go on the edge of a mirror, part of the beam is reflected, part goes straight. You use like really half of the beam goes straight and the other one is deviated. And then use two mirrors here to focus the beam on the sample. There are several techniques to see, to align in time the two beams. I don't want to, say too much on this. What I want to say is to be sure that the two pulses are coming together. What you can do once you have aligned it is to increase the intensity of your free electron laser to the top, and you write a real grating on your sample, okay? And that's what we have done. So using the top intensity of the free electron laser, you can write a grating. This is very useful to see that you align the two beams, but at the same time, you need to align the probe beam. And to align as a probe beam at the beginning, we wanted to use a tabletop laser because it's much easier. And you will see later on why we decide to go with this setup. And actually, you can align the tabletop beam by using this grating here on the sample. Then you have to do the experiment. You don't want to kill your sample and write in grating. So what you do, you reduce the intensity, you put fresh sample, and then you measure the first very nice spectrum coming out from transient grating. So, it's really ugly, this spectrum, okay? And with some imagination, we could see some Raman modes here and some acoustic those are the fluctuation you were seeing the figure before, very nice, using tabletop lasers. But I mean, referees from nature, they were trusting us, and actually they were right, because after some time we could be able to obtain a very nice spectra from those samples. So those oscillations are phonons, and also you may observe already right now a decay here. I will discuss this decay later on. I went very slow. Anyhow, this is a collaboration among MIT, PSI from Switzerland, and University of Trento. And then we decide to use as a probe the third harmonic of the free electron laser, because the free electron laser can produce a first harmonic but also a third harmonic. Okay, so then you pump your transient grating in the sample with the first harmonic, with the setup I was showing you before, and somehow you probe with the third harmonic, and we could see again oscillation in our system. To do so, we had to develop a beamline, quite complex. I don't want to go into the details, but actually at the end you have to align at the sample position 3 different instruments, okay, 3 different beams. This was quite complicated, but in the end we succeed, and we could measure phonons from a disordered system, a silicon nitride. Those are very, very recent measurements, not even published, and you may see the dispersion in energy, okay? But you can see also that there is a decay here. Questions? So the yellow region I was showing you before is basically here. So now we can access this region. As I said, this region corresponds to few nanometers, tenths of nanometers, and is kind of very interesting to understand phonon dynamics here. But you know, phonons, they are also heat carriers, okay? So they carry it in the sample. And in this figure here, that I got from a book which is entitled, I don't remember, I read it, "The Singularity is Near, When Humans Transcend Biology," you may see the number of calculations of processors as function of year and for $1,000. So you see that even today, if you want to spend $1,000, you cannot even reach the number of operations that a mouse brain can do. Okay, if you spend more, for sure. I mean, but this is just to tell you that everybody concerning the microelectronic devices engineering is pushing towards shorter, smaller and smaller gates, just to put more information and get faster answer from your transistors, okay, from your chip. The main problem is that when you go at the nanoscale and people is pushing in this nanoscale regime, you have to deal with the heat transport, okay? Because when you have phonons that transport heat, which are much, which have a mean free path much smaller than the heat region, then you are in the normal diffusive regime, and everything is very well known. But when the mean free path of phonons is larger than what of your heat region, hot region, sorry, then you are in the ballistic regime. I mean, the equations are not anymore valid. And in particular, you don't know how the heat is transferred in the ballistic regime. And this usually happens when you go at the nanoscale. Phonons, I mean, can travel much more before releasing heat, can travel much more in your sample than the hot region. So what you can do, you can measure how this diffusion or this heat transport happens in your system. And I was showing you the decay before in the spectra. Actually, this decay here is due to the thermal transport due to the phonons. So what you can do with this kind of technique, you can measure how the conductivity behaves at the nanoscale. because you can measure how the heat is transferred in your sample. And I think this is of fundamental importance for all these microelectronic devices industries, okay? So you can measure thermal conductivity at the nanoscale. This is kind of unique. Okay, so I show you before this sample here. Actually, transient grating is one special case of this kind of response of your system. And there are other cases. In particular, I want to concentrate on this one, which is called coherent anti-stock Raman scattering. Actually, people that developed this technique, I mean, they didn't call this technique cards, but after a few years, people was calling these cards. But these two guys, they were working in the scientific laboratory of the Ford Motor Company. This kind of funny thing to me. So the idea is of this nonlinear process is that you pump a vibration in your system. Basically, you use two pulses. The difference in energy of the two pulses correspond to a vibrational excitation. I mean, you don't know if it corresponds to, but you want to check if corresponds to. So you set the difference in energy, you imagine that you have a vibration in your system, and you go. It's like a Raman experiment, but now you are populating a vibration in your system, okay? Then, if there is a vibration with a third pulse, you will have the CARS, the coherent anti-stock Raman signal, in phase matching, in diffraction, at the given position, the given angle. So you are doing a diffraction experiment. So it's the same than doing a Raman, but Raman has not the capability to disentangle the signal from the noise. In this case, you have very big signal-to-noise ratio, okay? Because you put your detector at the phase matching angle, and that's it. You get only the good photons there. This is indivisible. Now, let's imagine to do an effort, theoretical effort, because now it's not yet feasible from an experimental point of view, and you do using free electron lasers. So now imagine that you have a system with different atoms, and you use two pulses. The two pulses are resonant with the core Hall excitation of your system. The difference in energy is a valence to conduction band. So you are creating an exciton. You are forcing all the atoms A to get an exciton on the A side, okay? At time 0, you coherently create exciton on all atoms A. So as Martina said before, exciton, they will travel in other places. So if I want to measure if I have any delocalization or any energy transfer to another atom, then I use another pulse which is resonant on a core hole of atom B, and then I'm going to fill up the hole in the valence band, and suddenly I get the coherent anti-stock Raman scattering in my detector. So this you can do in some molecule in the gas phase. This is extremely important because you have chemical selectivity, so you can decide on what atom I can create the exciton, and you can decide where you want to study the evolution in time of your exciton, if it's moving in another atom, in another again. So this kind of unique spectroscopy. And as I said, you can do in a gas phase molecule, but you can do also on solar harvesting devices, like in this case where you have a giant semiconductor nanocrystal on this MOS2 monolayer. So you can create your exciton on one of the atoms of the giant semiconductors and try to see how it evolves in time or it moves inside the monolayer. Okay? This kind of dream, we are working on this because you need 3 different pulses with basically free energy modulation and time delay. So this is not easy, but we are working in this direction. I can show you some results, but basically I will not do it because I want to conclude my presentation talking about proteins. 2 slides, okay? We started to say, it would be nice to measure structure of proteins, especially proteins that you cannot crystallize, okay? And you know that protein is kind of produced by the ribosome as a chain of amino acid. Then you have all these beta sheet and alpha helix and so on and so forth until you have the folding of the protein. What you can notice from the folding here in the picture, that usually you have two terminals, which are the N and C terminal. Many proteins, they have these two terminal outside. You can have some inside and so on and so forth. But the basic idea that we have right now, we are developing here, is trying to use what is called the binding of protein on a self-assembled monolayer. Basically, the idea is the following. Imagine that they have a protein, and I can link the protein on a self-assembled monolayer, all the proteins on the same site. In a way such that you have site-specific equivalent bond on a surface. In this case, you can multiply the intensity scattered from your free electron laser, or even by the synchrotron, by the number of proteins that you can align on the substrate. So we are working on this. Basically, what we're using is we're using several methods, but one of them is this protein splicing. Basically, you can produce a protein with expression of protein. You can attach to the protein an intein. Intein is nothing else than a segment of a protein. And then you can put the other intein here. And you know that intein, they produce this splicing. So you can attach all the proteins on the same C terminal on the self-assembled monolayer. So this is the way how you can attach together the proteins. At a given point, they should, we don't know, but we believe that they will align because the steric interaction. And this is one way to do protein scattering and then the determination of the structure. Okay, my talk is finished. So this was the last obstacle to the launch.